that's what we're working with today. Two heterozygous parents, when they cross, hear what they say. You got a 3-to-1 ratio of dominant recessive phenotypes in the progeny that's called traits are successive. When we are looking at the genotypes, that's 1 to 2-to-1. I'll show you how I got that, and it's really kind of fun. Each parent has a 50-50 chance for each allele, and the child gets from each a gene if case of I ideal. So 0.5 of one times 0.5 of the other yields a 25% chance for each genotype, brother. But you gotta remember that no matter what the order, both your heterozygotes won't have recessive disorders. Since no matter if the big A is first or second, you still have one of each allele, your dominant or recond. Mendelian genetics follow probability. You can use the hybrid cross to predict disabilities. All it really needs is a little manipulation. If you know the probabilities, then do the calculations. Genotypic frequencies will use the product rule. The sum rule for the phenotype's a really useful tool. Cause when you've got a lot of genes, like let's say 3 or 4, to draw a multi-hybrid cross would be too big a chore. Now watch what happens when we throw gene B in the mix. The cross is so much bigger, but we have a few tricks. We consider frequencies for each allele of gene B, and when you cross them out, you get the symbol 1 to 3. Here's where you use the product rule to find those frequencies. When you multiply the two quarters, you'll get a whole 16. That's the total different genotypes from A and B combined, and the phenotypes are 9 to 3 to 3 to 1 aligned. We multiply the likelihood of each for genotypes, and then add up all the cases for each separate phenotype. Cause no matter if you're het for both or doubly dominant, in the end it's still the dominant allele that's prominent. Mendelian genetics follow probability. You can use the hybrid cross to predict disabilities. All it really needs is a little manipulation. If you know the probabilities, then do the calculations. Genotypic frequencies will use the product rule. The sum rule for the phenotype's a really useful tool. Cause when you've got a lot of genes, like let's say 3 or 4, to draw a multi-hybrid cross would be too big a chore. A tri-hybrid cross with 3 genes, if you've got it fully drawn, 27, 999 to 3 to 3 to 3 to 1. Notice how the crosses keep getting 4 times bigger. 16 to 64 offspring when totally configured. There's a faster calculation using probability. You just multiply the chances for genes A and B and C. Let's say you only want the chances for triple recessive. Well, to draw the whole tri-hybrid cross would be way too excessive. We just take the probability of getting 2 small a times the probability of 2 small b's in DNA. Then the probability of having 2 sets of small c, and up with 1/4 cubed, that's a 64th chance, you see. The trick even works when parents aren't all heterozygous. It still uses the same product rule as we'll now discuss. Let's say you've got 2 parents with the genotypes shown. Here's a chance for you to really show us what you know. Mendelian genetics follow probability. You can use the hybrid cross to predict disabilities. All it really needs is a little manipulation. If you know the probabilities, then do the calculations.
Genotypic frequencies will use the product rule. The sum rule for the phenotype's a really useful tool. Cause when you've got a lot of genes, like let's say 3 or 4, to draw a multi-hybrid cross would be too big a chore.
Mendelian genetics follow probability. You can use the hybrid cross to predict disabilities. All it really needs is a little manipulation. If you know the probabilities, then do the calculations.
Genotypic frequencies will use the product rule. The sum rule for the phenotype's a really useful tool. Cause when you've got a lot of genes, like let's say 3 or 4,
to draw a multi-hybrid cross would be too big a chore.